Please let me know once my screen is visible.
Yes, we can see your screen. So you can introduce yourself and then can also start your presentation.
Yeah. So shall I start?
Yeah.
Okay. Thank you.
Stage is yours.
Thank you. Hello, everyone. I am Bhavna Aggarwal, Senior Member of Technical Staff at CircuitSutra Technologies. Through this presentation, I'll be talking about how to generate a hardware solution from a software implementation using high-level synthesis. The software implementation can be either in pure C++ form or a virtual prototype design modeled using system-level modeling methodology known as SystemC. The hardware solution here is digital solution for FPGAs or ASICs in the form of Verilog or VHDL. For our research, we chose a widely popular software algorithm known as SOBEL filter and generated a functionally correct RTL through it in the form of Verilog. Technically, we will discuss the efforts in migrating an open source image processing algorithm to a synthesizable C design using the HLS Synthesizable library and an HLS tool from Mentor called Catapult. As the efforts bore result, the next idea was to develop a synthesizable SystemC IP that encapsulates the SOBEL's algorithmic behavior. Lastly, we will also discuss about the verification process followed to functionally validate the generated RTL. In nutshell, the research intends to attract the attention of all the system and IP design engineers as well as verification engineers towards the benefits of high-level synthesis. High-level synthesis, also called as ESL synthesis or C++ synthesis, offers an automated design platform for developing scale algorithms that can transform to a hardware solution. It provides significant benefits over traditional hardware description language flows in terms of leveraging the software platform for implementation of digital solutions for FPGAs and ASICs. The designer typically develops the behavior and the interconnect protocol. HLS tools transform the untimed or partially timed functionality into fully timed RTL implementation as well as create a cycle-accurate hardware module. Using HLS, the design engineers can become much more productive by learning how to decouple design from behavior. It reduces the design efforts by writing up to 10 times lesser code and benefiting from 10 to 1000 times faster simulation speed. Many semiconductor companies are designing custom SoCs for emerging domains like vision, speech, video, or image processing, 5G, deep learning, artificial intelligence, machine learning, etc. In these domains, a lot of algorithms are already available as software implementation, either as free open source version or the companies have their own software implementation. Using HLS, designers can leverage the available software implementation to develop RTL designs much quicker instead of writing their whole code from scratch. HLS is just a high-level abstraction to both hardware and the software design phases, which aims to minimize the industrial gap between the two. Many companies like Mentor, Xilinx, etc. have come up with C++-based synthesizable libraries that provides constructs which can be used while developing the functional behavior of the algorithm. These constructs ensure that the software implementation can run through a tool called as high-level synthesis tool and automatically extracts an RTL out of it. The Accelera community has also come up with the synthesizable subset of SystemC, using which we had designed a SystemC IP encapsulating the SOBEL algorithm. Reusability of C++ test bench for RTL verification is another significant benefit of HLS to verification engineers that I'll be discussing in the later slides. Okay, As already mentioned, that for our research, we chose a widely popular software algorithm, which is an edge detection image processing algorithm commonly used for image segmentation and data extraction in computer vision and machine vision, where it creates an image emphasizing on edges. This operator, or also called as SOBEL operator, generates a 2D map at 2D map of X and Y gradients of image intensity at each pixel level, finds the direction of the largest increase from the light to dark, and rates the change in that direction. Here is an example starting image shown on the right, the gradients, and their filtered result. An open source C implementation of the algorithm is available on GitHub. Thanks to Sir Pedro Melgoyer and Alessandro Capitondi for the contribution to the open source world. The C-based software design from GitHub invokes the operator using the interface or a function called shown here. The function takes in 3 inputs in the form of RGB, width, and height. RGB is nothing but the binary data stream of the input colored PNG image. Width is the input for horizontal resolution. Height is the vertical resolution of the image. And the resultant output, the convoluted output, or we can call it as a gray data, is the filtered result of this operator. So to start with, we created 2 high-level synthesis implementation of the software algorithm. Firstly, the open source C implementation was modified to a synthesizable C design using the guidelines provided by the HLS Synthesizable library provided by Mentor. Then using the Mentor's Catapult HLS tool, the modified C design could successfully extract a Verilog RTL. The software design was converted to a hierarchical design with SOBEL filter function call as the top module. Function calls inside the top operator were marked as blocks, adding to the hierarchy of the design as submodules. The hierarchical design may contain few inline functions as well, if required. The hierarchical functions communicate through multiple channels known as AC channels in the Mentor's defined synthesizable library. Not all C, C++ pure constructs can be synthesized. And that's the reason that companies have come up with C, C++ based synthesizable library subsets. So there exists a synthesizable subset of the language that engineers utilize to write their code. Coding structures that can be synthesized includes system calls, inputs and output structures such as printf and scanf. There are other restrictions that like pointers and pthreads that are not allowed. As we all know that hardware is a static entity that serves to generate a well-defined behavior. Hence, no runtime dynamic actions are allowed. The software implementation of the algorithm tends to have pointers to pointers for interconnection and performance, which is not supported for RTL extraction. So we had to convert such members either to static arrays or AC channels based on their usage. AC channels are helpful in binding function calls as data streams from one function to the other. Likewise, any dynamic memory allocation or file IOs are not supported. Hardware should be aware of memory requirements. So any data to or out of the IP should be made available in internal or external memories. Floating point numbers in software are used to present higher range of values for accuracy and precision. Considering the hardware overhead for saturation logic of floating point numbers, C or C++ based float or double data members need to be modified to AC fixed or AC float synthesizable constructs. For commonly used math operations like square root, absolute, par, etc., Mentor's HLS library also provides equivalent math functions that can successfully transform to RTL logics. Hence, any C++ math operations used in the algorithm were modified to synthesizable math functions available in the AC math library. Unbounded loops, that is the loops which with termination condition dependent on some variable, are expected to give bad results. Such loops were were bounded using constant integers. Multiple same function calls, multiple call to the same function need to be distinguished using a template ID. This will translate to multiple instances of the same submodules. So in the last slide, I talked about the first version of the SOBEL filter synthesizable implementation. Now, the successful migration of the open source software algorithm to hardware solution led to the idea of having a SystemC IP that would encapsulate the functionality. Growing popularity of SystemC for systems and hardware designs motivated Accelera community to release a synthesizable SystemC subset. Following the guidelines in the subset and using the Mentor's Catapult HLS tool, we developed a subset compliant SOBEL SystemC IP that synthesizes to Verilog RTL. The system module encapsulating SOBEL functionality consists of multiple threads and methods. Each thread or method of the SystemC IP would synthesize to RTL module. As per the SystemC synthesizable subset, we followed few of the guidelines to create this synthesizable IP. Every thread and method should be sensitive to at least one clock and reset signal. Any output port being driven in the thread must be part of the reset block of the thread. Any loops used inside the thread or methods need to be bounded. Similar to C++ synthesizable design, we used static arrays that transforms to registers in internal or external memory, considering the memmap threshold configured inside the HLS tool. For sharing data across the threads or method, IP defines shared memory, which was available inside the Mentor's memory library. The memory is also called as CCS sample memory. For bit accuracy, it is advisable to use SystemC data types or AC algorithmic data types. Any math functions required were utilized from acmath.h library provided by Mentor. This is the block level view of the semiconductor design encapsulating SOBEL's algorithmic behavior. The IO logic of the IP consists of clock and reset input pins, an SOC bus consisting of write and read channel, where write channel provides the interface for the RGB input stream of any PNG input image, and the read channel provides output interface for the convoluted data stream as a result of the SOBEL filter image processing logic. There is a control signal to trigger SOBEL functionality once the complete input RGB stream is written to the IP's memory. As the image processing operation completes, an interrupt signal conveys the information that resultant 2D convoluted data is available for read. IP implements 4 memories, 4 CCS sample memories, segments of 200 by 200 size. The RGB memories stores the input data stream, and the convoluted memory contains the processed output data. The 2 high-level synthesis implementation we talked in the previous slides were called synthesizable because using HLS tool, these could successfully generate Verilog RTL in the form of Verilog. But does this imply that we have the hardware solution readily available? I think so. No. A design is a design that is not verified and validated is unreliable and non-serviceable for the purpose. Verification holds utmost importance both in the hardware and the software world. To validate intended design behavior, functional verification is the first and the foremost step. Considering the same, we ensure the following. Synthesizable C design and the generated RTL is functionally correct. Also, the synthesizable SystemC IP and the RTL generated through it was functionally correct. Now the question arises, how did we follow the verification? What was the effort invested? Did we write a separate test bench for each design? Did we write a UVM or a system Verilog stimulus to verify the generated RTL? Here are the answers. High-level synthesis provides a co-simulation verification environment, also called as SC Verify, that uses the same C++ test bench to verify both the hardware and the software behavior. Thus, one C test bench and one SystemC test bench is required to functionally validate the C design and the SystemC IP respectively, and the same test bench was utilized to functionally validate the generated RTL. Thus, no new UVM or system Verilog stimulus was required. So now let's talk about the simulation timings. The table here depicts the software simulation real timings for all the software version of the SOBEL operator executed using GCC. Undoubtedly, C being one of the fastest programming languages shall simulate the design in least time, clearly visible from the table. Synthesizable, C, C++, and SystemC designs, SystemC libraries add feature to pure C++ language, thus adding to the simulation timing. The table here compares the simulation timing for the hardware and the software simulation of the SystemC IP that encapsulated the SOBEL algorithm. RTL simulation is almost 3 to 4 times slower as compared to its software design. The RTL solution is cycle accurate. Also, memory read and write latencies add up to the total clock cycles during RTL simulation, thus resulting to RTL simulation to be slower. Now let's observe the RTL simulation timings for the two variants generated through two HLS synthesizable HLS designs. High-level design of SOBEL operator using QuestaSim. So these simulation timings are captured through RTL simulation using QuestaSim. RTL simulation here demonstrates that synthesizable constructs inside SystemC offers better performance than one available in synthesizable C++ library. Now let's discuss the efforts in terms of lines of code. This table outlines a number of lines of code a developer may write to develop various versions of the same algorithm. It is distinctly visible that the RTL code would be 10 to 100 times more than the software version. However, modification of pure C++ implementation to synthesizable C design is relatively simple, only 1.5 to 2 times effort required. All the results observed showcases how the design engineers can become much more productive by reducing their design efforts by writing up to 10 times lesser code and also benefiting from 10 to 1,000 times faster simulation speeds. The RTL generated with these steps was functionally correct. However, it will be definitely not in the usable format yet, as it is not fully optimized for the specific target implementations or for specific target applications. To get the optimized RTL, we will have to play with the HLS tool directives and constraints and may have to further refine the synthesizable code by using the optimization directives or tool pragmas at the right place. It also requires restructuring of the synthesizable code to capture a bit of macro architecture in the form of registers, memory, interfaces, etc. This exercise requires strong understanding of the RTL and cannot be done by the software expert. But the good news is that by now we already have a robust functional verification setup ready. And with each optimization iteration, we can quickly ascertain that the implementation, the C implementation, or the RTL generated RTL is still functionally correct. This cycle of refine, optimize, verify continues till we get the final RTL that meets the requirement. Till now, we could generate only functionally correct RTL, which needs to undergo a lot of optimization and refinement for power performance analysis to be for a target application form, which is achievable using HLS tool directives, constraints, and code restructuring for macro architecture. Apart from this, there is another scope to the study, which involves explaining the SOBEL's SystemC design to use synthesizable hardware components or functions in the NVIDIA's open source HLS library named as MATLAB. These are the two areas which are planned for further exploration in high-level synthesis and ESL domain within CircuitSutra. I hope till now I could eliminate the benefits of high-level synthesis in terms of automated RTL generation from an open source C++ design and providing a co-verification platform for functional equivalence of the software versus hardware. To emphasize, a software practitioner can easily take the original software implementation and generate a functionally correct RTL without requiring in-depth knowledge of it. They just need to understand the synthesizable subset guidelines, which are actually easy to understand. To maximize the HLS capabilities, both software and RTL design engineers can collaborate to develop the ASIC or FPGA solution at the earliest. Also, software test engineers and RTL verification engineers can collaborate to validate and verify the solution in parallel, thus minimizing time to market by apportioning both design and verification responsibilities. Thanks for your time, everyone. I'll be happy to answer any questions.
Thank you, Bhavna. So do we have questions? Maybe we can start with the first one. Your main focus is the design of IPs, or do you also have intention to consider a whole SoC design?
We focus on design of IPs as well as design.
So the both. Because usually the complexity of SoC, complete SoC will be quite high. So do you have already any experiments concerning the whole SoC?
Like in the domain of virtual prototyping or in the domain of virtual modeling SystemC, we do have that experience. But in the domain of high-level synthesis, still that is an exploration area for us.
Okay. And also, when you are reusing your test bench, your verification environment, different levels. So do you have also to update this verification environment manually, or is also from different levels you can reuse without any updates?
Yeah, we don't need to modify the test benches for the verification. So we can use these at any level for verification. So basically, no modification inside the tests required.
Okay. So we have also a question in the chat from Dukmin. What do you think about accelerated machine learning algorithm using high-level settings? Any advantages or disadvantages?
Like as per my research or as per the study, accelerated designs for machine learning and using HLS, that would be definitely a benefit. It will actually accelerate the whole performance, design as well as verification in the design and verification domains.
Okay, but there's also a one way to use to design actually machine learning IPs using high-level synthesis could be at least for the initial evaluation could be also very benefit, right?
Right.
Yeah.
Absolutely.
Yeah. So do we have more questions? So otherwise, I'd like to thank you, Bhavna.